Okay, in this presentation, we'll be talking about how to work with sound files, how to create sound files, and how to compress. Okay, first of all, in general, there are two types of file compression algorithms. Uh, in one type, no information is lost whatsoever. That is, the new file that is created is smaller than the original file, but has the exact same information on it. The other type of file compression, called lossy, means that some information is removed from the file, and that's how it's made smaller. Now, you might wonder what the advantages of one over the other is. Well, for example, if you're sending a text file, lossy compression is difficult because you're actually removing the information, and you pretty much need all of the information in a text file or a data file, okay? So you can use lossless techniques for text files and data files, which don't tend to be that large anyway. And by the way, there are ways to compress data files and text files that are lossless. Unfortunately, we can't cover that in this particular lecture, but there are lossless techniques that are used for data files and text files because they're, you can't really lose the information. Now, lossy methods, on the other hand, are needed when you really need to really compress the file, make it much smaller than it originally was. Now, you always must remember that the smaller file must be of sufficient quality that it meets the requirements of the application. I'm sure you've all seen videos that are so bad or audios that are so bad that you can't make them out, you can't understand them. That, of course, is undesirable. So it's very important that your final product, when you're compressing a file, still meets the requirement of what you're trying to do with it. Now, lossy methods work really well for things like sound and images because, again, these are the largest files that we have, and so it's really important that we do something to make them smaller. And also with sound and images and video, the mind can fill in the blanks. Now, I'm sure all of you have seen, when you go on Google Maps, first it's kind of fuzzy, and then it's a little clearer, and then it's a little clearer, and then it's a little clearer. Okay, well, you can still make it out when it's pretty foggy. And so, depending on what your application is, you may be able to use a smaller file. So again, when it comes to really big multimedia type files, we really need to use lossy compression. Okay, the standard compressed audio file format that we're using for audio files, and pretty much universal, can be easily sent over the internet and read on any type of computer. MP3. Now, MP3 is derived from a group of people many years ago who put together this group of standards, and they were called the Moving Pictures Expert Group. And originally, this file format was called MPEG. And then it evolved into MP2, and then MP3, and now, of course, MP4. So this is a lossy type of compression. And what it does is it uses inexact approximation of the information, thereby discarding part of the information to reduce the file size. Okay? Now, again, this is for audio files. For video files, MP4, which is QuickTime, AVI, WMF. There are several formats that you use, but probably the best one to be most universal is MP4. And again, these are lossy techniques. Now for still pictures, still pictures, of course, are one of the oldest things that we had on the internet. And so we had originally two standards, GIF and JPEG. And they really show you two different ways of approaching compression. In GIF, which is a format that limits you to a number of colors. Originally it was 8 colors, then 16, then 32, then 64, etc., etc. Now it's quite a large number of colors. So by reducing the number of colors in an image, it reduced the file size. but it worked very well for graphics, but not so well for photographs. So a group got together, a group called the Joint Photographers Engraving Group, got together and set the JPEG standards, which is now reduced to JPG. And JPEG compresses files by removing unnecessary information. When you see a photograph coming in over the internet, now not a graphic, a photograph, and it comes in stages, first it's kind of low resolution, then it gets higher, then it gets higher. What's actually happening is those are the JPEG layers loading in. Okay, so by reducing the resolution of the image, you obviously reduce the file size. Now, of course, you have to make sure that the resulting image is still good enough to see. Now, we used to have to choose, well, do you want to do JPEG, you want to do GIF, depending on what kind of image it was. If it didn't have a lot of colors in it, you could do GIF and really still, and by the way, GIF or GIF, I pronounce it both ways. Now, probably the emerging standard is PNG, or PNG files, and PNG is lossless compression. That is, it gives you the best of all worlds, allowing as many colors as you want and not losing any details when it compresses the file. One of the major problems in representing information on computers is that the world around us is analog, and computers are digital. So in order to get information onto a computer, we need to change it to the zeros and ones that a computer understands. So, for example, words are represented on a computer by using things like the ASCII code that converts a letter, which a computer doesn't understand, into a number that the computer does understand. Now, this has to be done for virtually every kind of data that we store on the computer: text, data, video, audio, so on and so forth. So the question is, how does one convert an analog signal that you find in the world into the digital representation that can be stored on a computer? Now, if you don't convert the analog data to digital data, of course, it can't be stored and manipulated on a computer. And manipulation is very important. In order to be able to edit sound, in order to be able to edit a Microsoft Word document, it needs to be stored on the computer. And of course, in order to do that, it has to be converted to digits. Now, analog data is continuous. That is, at any given point, it's hard to tell exactly what the value of it is, whereas digital is discrete. Think about a regular watch, with a hand on it and clocks and arms and stuff, versus a digital watch. When you look at a regular watch, you can't really tell exactly what time it is to the second because it's always moving. By the time you say what time it is, it's moved on to the next time. Now, a digital watch, on the other hand, is always very precise, sometimes to hundredths of a second. And it's always exact, discrete, this is what it is. I don't know if any of you are old enough to remember the old analog gas pumps, where the dials actually used to spin as you pumped gas. And again, they were always moving, continuously moving. Therefore, it was really hard to tell exactly what it was at any given moment. Now, human beings kind of make the assumption that because something is more precise, like digital, that it's more accurate. Clearly, that's incorrect. Digital watches do not keep better time than regular watches. Okay, it's just the appearance because we're looking at discrete signals, and so when we look at the gas pump and it has digits telling us how much we spent and how much gas we pumped, seems pretty accurate to us. It tells us, oh gosh, we pumped an extra 300th of a tank of a gallon of gas. But just because it's precise doesn't mean it's accurate. Now, for audio, we are dealing with sound waves. Now, you all know what sound waves are. And sound waves must be converted to discrete numeric data. The process of doing this is called sampling. Okay, let's take a closer look at sampling. First of all, you start with a sound wave. Now, you all know what sound waves look like. You've seen them. You've seen them on oscilloscopes and TV and so on and so forth. And it is what we call a continuous signal. Notice that it's curving. It's a little hard to tell exactly at any point where you are. The challenge here is to sample that wave and to convert it into a digital representation. So in order to do that, we can develop a little scale here, put it on a little horizontal and vertical axis. And on the left-hand side, we can develop a numeric scale. Now here I have integers, 1, 2, 3, 4, 5. Obviously, these could be much more precise to hundredths or thousandths of a place even. And of course, on the bottom represents the passage of time. It's one of the things I learned when I was a psychology major is that time goes from left to right. That's kind of an inside psychology joke. Sorry about that. At any rate, as time passes at any given point, you can take a sample of that wave. That is, at a given point in time, measure the amplitude, the height of the wave. Okay? When you get to the height of the wave, you can then read across to your numeric value. So what you have done here is you have converted an analog signal, a wave, into a discrete number. But notice that that number only represents one point in that wave. It is not a very good representation of the wave. Now, if you want to have a little bit better representation, of course, you can sample more often. Again, each time reading across the amplitude to the numbers, and each of these then could be converted into numeric values, and we would have a much better representation of the wave. But look at how much information we have lost. Okay? Even though we have sampled the wave many more times than in the first example, we still have much data that is lost. So what's the solution? Well, sample more often. Obviously, the more often you sample the wave, the better the numeric representation is of that wave. Now, how often do you have to sample a wave? Well, to give you an example, a CD, an audio CD, the wave is sampled 44,000 times per second. Now, with this example, you're seeing very low numbers, but imagine 44,000 measures of the wave. Okay? And even with 44,000 measures of the wave, just like in the examples above, some information is lost. Whatever happens between samplings is lost information. However, most of that information is beyond the scope of the ability of the human to perceive it. So it's not really a problem. Pure audiophiles will tell you that nothing reproduces sound like vinyl, old-fashioned records. Why? Because no matter how often you sample the wave, you're still losing information. Okay? By the way, the two factors that determine the file size is the number of times you sample and the accuracy of your measurement. So if each of your measurements, in this illustration, I'm using integers. That's ridiculous, of course. It would be, very large or very small numbers. And that bit depth, in other words, how many bits are used to represent each number on the scale, will also influence the file size. So it's two things. It's a bit depth and the sampling rate. Well, let me tell you how I got started thinking about all of this. I finished a podcast that I was doing for a class. It might have been this class, I don't recall. And after finishing the podcast, and so, after I saved the podcast, I went to export it as an MP3. Went to the file menu and went down to export. So, of course, then I, did the normal thing. I went to name the file, and I went to save it. And, of course, I wanted to do it in MP3. I selected MP3 from the drop-down menu. If it's not already the type that's selected in the box, then you just go ahead and, you use the drop-down menu and select MP3. So I went ahead and did that. And then because I'm always concerned about file size and things that are going to be uploaded to Blackboard or sent to students. So I decided, well, let me go take a look at how big this file is. So after I exported it, I went to the folder that it was in, and I found it, and I right-clicked on the file itself and selected Properties, and I noticed that the file was almost 48 megs long. Now that's quite a lot. Think about if you have a 5 megabaud download speed, it's going to take you quite a few seconds to download. Now that doesn't seem like much in this day and age. And of course, if you have a 50 megabaud or 100 megabaud connection like I do, maybe not significant, but you know, that's a pretty big file. So I wondered, well, gee, I wonder if I can make it smaller. So I went back to the Audacity program and decided to try to see if I could figure out a way to compress the file a bit. So I went back to the export function of the file menu. But this time, rather than clicking on Save, I clicked on the Options button. Okay, so I noticed that the quality is set to 32 kilobaud. Now, quality, if you recall, is the result of the bit rate and the sampling rate. Okay, so I'm cutting that in half, and hopefully that should lower the file size and not change the voice too much, so that it's still usable. So what I did is I just knocked it down to 16. That's about half. Now, when I go to save the file, I want to rename it because I want to keep the original MP3 file intact. That way, in case this doesn't work, in case I knock the sound resolution down too much, that it doesn't sound right, I want to be able to go back to that original version and work on it some more. So I gave it a new name. I just added the word small at the end to let myself know that this was the smaller version. And that way we will keep the original version without any problem at all. Okay. You'll be then given the opportunity to store some metadata about the file. Metadata, of course, is data about data. In this case, data about the recording. If you ever wondered how a radio show could find a clip, an audio clip from years ago that they decide they want to replay for some reason, this is how. All of the things that are on the meta tags are things that are searchable. You can't search voices. You can't search images. So the ability to add meta tags is very important in situations where you want to be able to find this recording again. We're not going to really deal with meta tags right now, but it's really important that you understand what metadata is. So just go ahead and press OK. Now, when I did that, I saw this screen that said I had chosen an invalid sample rate. I don't know why. But if you see this screen, I decided, well, okay, I can chance to lower the bit rate a little bit. Okay, and you can see the sample rates here is 2400. I'm going to lower it down to 1100. And again, I'm going to check at the end and hope that the new recording, the smaller version, will meet my requirements. And of course, the file was saved. Now I basically did what I did before. I went into the folder, found the file, right-clicked on the file and chose Properties, and look, only 5.99 megabytes, quite a bit smaller. And so we can clearly see the effect of file compression by lowering the sample rate and lowering the quality. Remember our original file, 48 megabytes almost. Our new compressed, smaller version, 5.99, you can do the math, it's significantly smaller, 4 or 5 times smaller. Now, keep in mind here that the reason that we're able to do this is because it's a voice recording. And voice recordings do not need to use all of the power of MP3. It's not high-fidelity music. Obviously, when you are recording a high-fidelity music, you're not going to want to reduce the quality, okay? But a voice recording, you often can. Now, you must listen to the new, smaller version compared to the old one and make sure that it is of sufficient quality to meet your requirements, okay? Without that, it doesn't do any good to compress the data if the data is not usable. Okay, so if it isn't, go back to the original, try again, maybe just use your original, or maybe try a more intermediary sampling rate. At any rate, you have to experiment with it, and hope you found this information to be useful. Have a great day, and if you have any questions or comments on this PowerPoint presentation, please let me know. I appreciate any feedback.